Well, good morning. Today we will deal with the preliminary design calculations of cable-stayed bridges. On one hand, these preliminary calculations are rather important to understand the inner flow of forces and the inner working of a cable-stayed bridge, which, in addition to all the structural details we have dealt with until now and the on-site considerations we will deal with in the next semester, it is important to understand the inner flow of forces. And to my experience, that is most easily done by doing these hand calculations, let me call them. Once you understood what we are doing, it is rather simple, I always feel. On the other hand, it needs a certain adjustment of thinking, of getting this, on the first glance, complicated, highly statically indeterminate system of a cable-stayed bridge down to a similar, approximate system which is statically determined and which we can calculate. Well, I did it initially with a slide rule. When I started, there were no electronic pocket calculators. So I'm not asking you to go back to the slide rule, but I assure you, all the calculations we do with a handheld pocket calculator. We don't need any programs for that. In the script, there are the complete examples with all numerical calculations from beginning to end. We have here a part of it today on the slides. I've taken care to try and get it in a way that it's easily understood. However, I'm pretty sure I can give you here today how the calculation goes. I cannot go into all the numerical details. I feel it is important for you that you load down from the university intranet, as you know, the lecture 11 and 12 I have today, and follow in detail, figure by figure, what I've calculated there. And in my experience, once you've done that, you say, well, it's simple, there's nothing to it. But there is no way around that you sit down quietly for 2 hours or so and go through. I try my best, again, to show you the basic ideas, but we cannot go here figure by figure, I repeat. That's a task you have to do yourself. There will be a sort of repeat of what I'm going to tell you today as a preparation for the examinations. And as after every semester in February this year, it is February 14 from 9:20 to 12:40, I will give what we call in German Repetitorium, which I would call in English a refresher course, where I go in detail, basically, again, through what I'm explaining to you today, and, which is also of importance for every student, the major part of the examination, 40 minutes of the 1 hour, will be a preliminary calculation of a cable-stayed bridge, very much along the lines I'm outlining here today, and I'm repeating in the refresher course on February 14. So I'm very much convinced, if you listen today, sit down for, say, 2 hours at home and go through the script with the detailed calculations, and then sit in the refresher course, you will understand it perfectly and you will have no problem doing the examination. And that is my experience. I've taken now 3 examinations and all the students did very reasonably in doing this calculation. Now, let's get into it. We will talk basically about a typical concrete cable stayed bridge, the preliminary design, and a typical steel cable stayed bridge. It differs in the determination of the moments under permanent loads. Now, we start with a typical concrete cable stayed bridge and look at the system, a simple system, a symmetric cable stayed, 3-span cable stayed bridge. Now, for symmetric loads, which we are considering here, we can use 1/2 of the bridge, and we have a side span and a main span with 54 or 67.5, the 1/2 bridge. It's a tower with vertical legs. We use a simplified concrete cross-section, a double T-beam. If you see here, we'll see it later in some detail. And important for the calculations, if we consider cable stayed bridges with 2 cable planes, as we normally do here, we calculate all the moments and cross-section properties for 1/2 bridge or per cable plane, CP. It's from my experience over years that if you don't do that very rigidly, you very quickly end up with a factor 2, and you don't know was it for the whole bridge or the half bridge. So I recommend to you strictly per cable plane everything, then you avoid the mistake of the figure 2. For all the examples we are dealing here with in the lecture and in the examination, we always use the same cross-sectional values. They are given, so we don't want to fiddle around. That's just a basic thing. Basically, we use either parallel wire cables with 7 millimeters, and that's the area. We reduce the effective modulus of elasticity, which is 2.05, as we know, a little bit for the sag, but the sag is small, so we use a constant 2. That's a regular steel. 45% of ultimate is, we do everything at service load, is permissible stress 752 Newton per square millimeters, and we have a fatigue range possible of 200. So that will be the same for all the examples. We can also do alternatively for parallel strand cables. Well, that's a little bit different steel, so we have a little bit higher permissible stress, and we have another area, but basically that's the same. Concrete beam, we assume, is concrete B45 with a modulus of elasticity, and service load stresses I give here from old codes. I mean, normally we do final design at the ultimate stage with load factors, but we remain here with permissible stresses at service. That's easier for a preliminary calculation. And we have the section properties. One little difference, what we call in German Widerstandsmoment, and use a W, in English is section modulus, and we use an S. So the large S, top ST, section modulus at top would be in German W oben and S bottom. Otherwise, we have a little bit different nomenclature. Our dead load, small g, is DL, dead load in English. And the Verkehrslast is life load in English, LL, simple rather. Now we have two types of loadings, uniformly distributed load, which we call in English UDL, from uniformly distributed load. And we have a track load, which we can, our SLV is a track in English, and we can also call that a concentrated load, which is abbreviated by CL. And there's then one other difference. The stresses we call in German sigma. In English is always a small f. FC for concrete stress, FS for steel stress. Otherwise, it's very similar. But that is the way things are done. I've done calculations, design calculation in English for many years, and that's the way you just do it. Otherwise, you don't understand. So, now we have the system, section properties, and loads, and now we look in the calculation into the calculation of the normal forces. Now, for the calculation of normal forces, meaning cable forces, normal forces in the beam, and normal forces in the tower, we use a system which has basically the same deformations than the true system, which means we use hinges in the beam where the cables are connected to the beam. So we take away the moment capacity of the beam, and we take away the fixation here and introduce a hinge here. So a hinged or articulated system is our approximation for calculating the normal forces. The moment we do that, we have a statically determined system. And we can do it because the deformations of a cable stayed bridge are governed by 95% by the stay cables. So we make only a very small mistake in the range of 5% if we take away the bending capacity of the tower and the beam. And I repeat from earlier lectures where we had all this in principle, which we now do with figures, if we have a vertical force here, then the cable component, if we assume all this is hinged, is the force divided by the sine of alpha. That's the basic formula with which you can more or less calculate all the normal forces of a cable stayed bridge. It is also true, of course, if we calculate this support reaction here, that then the backstay cable force is the support reaction, the vertical, divided by sine alpha. So with these formulas, we basically can then calculate the cable forces and the horizontal component of the cable force, meaning cable force times cosine alpha, gives us the normal force in the beam. And the normal force in the tower is basically the support reaction of a statically determined system which consists of a simply supported beam with a cantilever. This is the simply supported beam. We have here the support reaction at the hold down pier and the support reaction at the tower. And this is the cantilever which, for symmetric loads, which we consider, we can cut the bridge in the middle. So that's all there is, statically determined systems. And I think that's basically it. The dead load arrangement and distribution is a special we will come to. The life load is very easy. We have basically two life load cases. One, full loading of the main span, and the other one is full loading of the side span. That gives us a normal force increasing from cable to cable up to here remains constant. Gives here a tension force and a compression force in the cable. I've outlined all that to you. Now, we calculate the stay cables, and there again we have to consider, first of all we go into the backstay cables. Now, the deformation and basically behavior of a cable stay bridge is governed by the backstay cables, because the backstay cables keep the tower head in place, retain the tower head, to which all other cables run. So the movement, deflection of the tower head governs the deflection behavior of the whole cable stay bridge. I repeat, the backstay cables govern the behavior of a cable stay bridge. They have three types of loading. The dead load is of course always over the full length of the bridge, but is split up in parts. We come to that in the next slide. For those dead loads which are governing for the backstays. Now the life load is rather simple. The biggest tension force in the backstay cable comes if we load the main span with the life load plus the concentrated load, the track, or the biggest compression force in the backstay comes if we load the side span and set the concentrated track load in about the 1/3 point. Now we look into the dead load moment distribution and calculation of the backstay cable forces from dead load. Now, here we have spread out the dead load as it is on the beam. No discussion, that's there. Now, first of all, we say about 1/2 of this distance between the backstay and the first cable here, 1/2 of that goes directly as compression into the hold down, is out of the system. And then this remaining part here, from here to here, is balanced between these two, does not go into the backstay cables. But what remains for the backstay cables is the unbalanced part of the life load, of the dead load, here in the center. So we have here 3 times 18 meters, 9 meter, 1/2 of that goes directly into the support hold down of the hold down pier. Then remains 45 meters to the tower, balancing the other 45 meters on this side. And what is remaining then of the total length is 22.5 meters dead load, which go directly into the backstay cables, which stress the cables under permanent loads, which is very important, because if we later have life load in the side span and I say there is compression in the backstay cables, well, then it means a reduction of the tensile force from this part of the dead load. Now, how do we calculate that? Very simple. We have a simply supported system with a cantilever, and we want to calculate this vertical reaction here in order to be able to calculate the cable force. Now we build the moments around, sum of moments around tower to be 0, very basic support reaction calculation. And then we have here this 128 kilonewton per meter is the dead load, times the length of 22.5 meter, times this lever arm divided by this lever arm from sum of moments. So we arrive at a vertical R retaining force of 3,000 vertical, and then we know the corresponding cable force is the vertical support reaction divided by this sign. So we have a 6,700 kilonewton backstay cable force from dead load. This is important. Look at it in the script and understand it. It's more or less a very basic consideration for the understanding of cable-stayed bridges. It's simple, but you've got to get the hang of it. Now, what life load for what cable forces go into the backstay cable from life load? Well, full load of the main span. Well, then we can calculate this support reaction again. The length, 67.5 meters, times the dead it's not dead load, it should be life load. I'm sorry, that's a mistake. The life load is 11.5 kilonewton per meter, again, times this lever arm divided by this, gives us 902 vertical component. It's the support reaction from this life load arrangement. Now, if we put the life load here, we have a simply supported beam, so 1/2 of this and so on goes in compression into this support reaction. Now, which means the highest tensile force from life load is this 902 kilonewton divided again by the sine, and the biggest compression, so to say, from life load in the backstay is this 561 divided by the sine, gives this. Now we have the three components of the backstay cable forces from dead load, permanent load, maximum life load, and minimum life load. And that's what we need to size the backstay cables. If we use parallel wire cables, now we size for tension and for fatigue. For tension, we size by adding the dead load cable force plus the life load cable force divided by the permissible stress, which I showed you earlier. So we require 11,000 something square millimeters for the biggest load. Now we have to check for fatigue load. Now the fatigue load is the absolute of the maximum and the minimum life load from the two load positions. We had plus 2014 and minus 1200 as compression, so that's the range. And we divide, in this case, by the 200 Newton per square millimeter permissible fatigue range and see what the required area for fatigue is. In this case, I've just made it as an example. Fatigue would be governing. We need 16,000. Normally, this will not be the case because I have used the full life load. However, in reality, we only use 50% of the life load for the fatigue range, but this would be the two possibilities. Now, if we have the 16,000 something square millimeters required, we divide by the area of one 7 millimeter wire, and we need 425. Okay, and we have with the wires a little special thing that we use them in a hexagonal arrangement, which needs, we have only in 6 steps, 6, 12, 18, plus 1 in the center, we use in the wires. So the total is always, the number is 6x plus 1. Okay, and for this, we would then get a certain amount of wires. We can do the same for strands and arrive at the same. Now, the sizing is not a problem. So we do the same. We've sized now the backstay cables for per maximum load and fatigue. Now, for the forestay cables, it's rather simple. We just have the cable distance times the life load plus the concentrated load divided by sine. Alpha gives us the cable force from live load, and there is no negative influence line of the cable force, meaning we do not have compression from any live load position as we have in the backstay cable. The backstay cables are the only ones in this preliminary calculation which get compression. So there we have just a size for the maximum tension force. That is a very straightforward, rather simple operation. So in this way we can size all the stay cables. Simple. Simple, n'est-ce pas? It is simple. Just go through the figures. Now, we look into the normal forces of the beam. There in the lecture before, I gave you a complete formula if we have the live load and the dead load here over this system. Can do it directly, and we arrive at the maximum compression from dead full UDL, full uniformly distributed load of 11,000 at the tower. We can add the component from the track load, from the concentrated load. Of course, there then, if we have this vertical, we want this, we have to multiply, we have to use the tangents, the tang alpha, but that's very simple relationship. And finally, we have the normal forces in the cables, the normal force in the beam, the maximum, and the normal force means in the tower. Well, we just load our statically determined system with the full dead and live load and form the moments around this support reaction equals 0. Okay, then we have just to take this whole thing and we arrive at the support reaction here of our second support, very simple, which is normal force in the tower. Okay, now this was determination of all normal forces in a cable stayed bridge for a statically determined system. Now we come to the calculation of the beam moments, tower moments. That's the second important step, sizing the beam. There we use a different approximation. Naturally, we cannot use an articulated system, a beam with hinges. I mean, we need the true beam stiffness. First of all, permanent loads, always important. I told you earlier that for a concrete cable stayed bridge, we choose the moments under permanent loads as those for a beam rigidly supported at the cable anchor points. We can achieve that by pulling at the cables in such a way that we reach this stage. I've explained all that to you. So, we know already the positive moment is dead load times cable distance squared divided by 24 in plus as this positive and this as double negative moment. Very simple, simply supported beam. Continuous beam on rigid supports. The live load, we use another approximation. We say, okay, we have here our actual system, which is equivalent for the beam for the beam moments for a beam which is on steel springs with the same elasticity as the stay cables. And in the next step, we distribute the discrete springs continuously over the lengths. And then what do we have? we have a beam on elastic foundation. And thank God some wise guy calculated for us the moments for a beam on elastic foundations. Basically, we have to calculate the characteristic length L. And from that, if we have that, the moment of a beam on elastic foundation is for a concentrated load, is 1/4 times this concentrated load times this characteristic length L. And for a uniformly distributed load, it's 0.161. If we integrate these strange thing, then we come to this 0.161. That's as simple as that. Times uniformly distributed load times this characteristic length square. So, in order to calculate these moments, we have to calculate the elastic length L. And since you probably believe more in computer calculations than in my word, I have here a comparison made of the influence line for the same cable stayed bridge, influence line calculated for a beam on elastic foundation, the way I've told you, and the influence line for a beam moment computed calculated by computer. And you see it's very, very close for the positive moment. So it works. It's not so good for the negative moment. There, the approximation with a beam on elastic foundation is not good. We don't need it for preliminary sizing. I just mentioned it. It comes up later. So it works. Now, how do we calculate this elastic length, which we need? Well, we use the following parameters, and I always found it helpful to make this little sketch. I write here the steel area. I write here the cable force from 1 and the length. One step back. How do we calculate, or in order to calculate the elastic length, we need to calculate the deflection at the point we are looking at. It's not constant. And how do we calculate this deflection? And then by placing a unit load 1 onto this point and coupling it with the unit force 1. So we need, for the calculation here, we need always the steel area, we need the force in the cable from this force 1. I've shown you how to calculate it, being simply supported. And we need the length. The length is the horizontal divided by the cosine alpha. The cable force is the vertical component, or this support reaction, by the sine. We know that, and so we can then easily calculate this force here by the as we had it before. And then if we want to calculate this deflection here, delta, then we use, as I've explained already also, we combine the one with itself, so we have the square of the cable forces from the load 1 times the length divided by the E and the area of the stay cables. We do that for the forestay, the 2.44 force squared times length divided by EA, and we do that by the backstay, the 2.48 squared, and so on. And we end up, I'm sorry, go away. We end up for a unit load of 1 meganewton, we have a beam deflection in the center of 35 centimeters, 0.352 meters. And then we can say the elastic support is this delta divided by the cable distance is so and so many meganewton per square meters. And then finally we come to the elastic length, which it's not bad, it's badly done. It's the fourth root. It should be hopefully written better here. That's people, we all like to make a mistake here. The fourth root is very rare. So if you calculate it, take care that you really take the fourth root and not the square root or something, as one normally does. So I just pointed out. So we have to calculate the fourth root from the beam, of course, now, modulus of elasticity, the beam moment of inertia, and the elastic support. And then we come to something always in the range for typical cable stayed bridges. 20 meters is the elastic length. And then it's easy. We just have, we calculate, let me just see. Somewhere, don't know where I have that. If we then put our loads and the length in here, we end up with the beam moments, and we can calculate from the dead load and the live load beam moments divided by the section modulus, top and bottom. We can calculate beam stresses minus 5.2 and plus 8.7 in the bridge center where the normal force is small. We can also calculate the compression at the tower for the normal force which we calculated. That's simple, but we look at the center of the beam. We have plus 8.7 tension. Now we like to put in pre-stress to overcome this tension, so there is only compression. And you remember from an earlier lecture, if we post-tension a cable-stayed beam with straight tendons, then the eccentricity moments and the restraint moments balance one another, and all what remains is central compression. Doesn't matter where the straight tendons are positioned in the cross-section. Explained to you? So, if we have a tensile force of 8.7 from bending, and we want to get this tension out, then we superimpose post-tensioning compression of 9 meganewton per square meter. And if we add the two up, then we have here plus minus 9 gives us minus 0.3. And if we have on the top minus 5, minus 9 in post-tensioning, we are in minus 14.2. Earlier we've said we permit an edge stress of minus 17, and so we are below the permissible compression stress in total, and we have no tensile stress. That simple is a sizing in bending of the beam of a cable-stayed bridge. Of course, for this calculation, it doesn't matter whether we have concrete or steel. Concrete and steel is only different in the permanent load situation. Now, we come very briefly to the tower moments. I've shown you how to calculate the beam moments. The tower moments are basically governed by the deflection of the tower head from live load in the main span, or from live load in the main span gives us tensile force in the backstay, which elongates the backstay, and by elongating the backstay, the tower head is shifted, and then we have a cantilever with a forced deflection at the top. We can easily calculate the moment. How do we calculate the tower head deflection? Well, we have to combine the loading, live load in the main span, which we know gives us the biggest sag in the main span and the biggest movement of the tower heads to the inside. And how do we calculate it? Well, we combine again the actual loading with the unit load in the direction of the deflection. So we have to calculate these. This is the cable force from the two. We have to multiply the cable force from the load with the cable force from the unit load times length divided by EA, always the same. So we know the tower head is deflecting by 4 centimeters in this case. We have very strong backstay cables. And then, of course, we can calculate the moment for a cantilever. It's this delta horizontal deflection times 3EI divided by L squared. So, I've shown you how to calculate the moments of a cable stayed bridge by the beam moments and a permanent load. We have the rigidly supported system, QL squared 24th. We have the live load moments from an elastically supported beam, which is depending on the elastic length. And we have calculated the tower moments from the deflection of the tower head under live load in the main span. That's all we need. And of course we had the normal forces for these, and we can combine them. We can calculate the stresses. We can, for the bridge beam in the center, superimpose post-tensioning, just the compression force, by, for example, the condition no tension at the bottom and within the permissible range of compression in the top. Together with the sizing of the stay cables I've shown you before, that's all we need to preliminarily size a cable stayed bridge. And the detailed computer calculation, which of course will always be done, shall not give significant differences. Thank you. In the first part today, we dealt with a cable-stayed concrete bridge. In the second part, we will deal with a cable-stayed steel bridge. The difference is in the determination of the permanent load situation. You remember, the permanent load situation for a cable-stayed concrete bridge we chose as a beam rigidly supported at the cable anchor points because only this system, this run of moment, is not subject to moment creep. If we use for permanent loads a different system, then the moments creep away. I've given you all that, and we have to cover two dead load moment situation together with live load. It's ineffective, requires too much material. Now, a steel cable stayed bridge is not subject to creep. The beam of a cable stayed bridge is not subject to creep. Therefore, we can choose a different permanent load situation. It's important that you remember that, the basic difference. What is our desired run of moments for a steel beam? Well, it's that run of moments which, together with the live load and all the other temperature and things, requires the minimum amount of steel. We want to design the most economic cable stayed bridge. In concrete we can't help, there we have to stick with the rigidly supported. In steel we are free. And so we try to find a run-off moment under permanent loads for a steel bridge which in combination gives the minimum amount of steel. Well, how do we go about it? That's what is basically what I'm going to show you now. We use, as an example, a cable-stayed bridge in Stuttgart-Schillersteg, very early cable-stayed bridge, which has a few cables there. It's a very simple, symmetric steel beam with a top flange and a bottom flange in steel, and it's stiffened. But basically it's symmetric. There is the beam parts in two parts here, but we only look basically at this part as an example. Now, again, we need, of course, cross-section properties and loads. We use here, but that's some steel 37 with a permissible stress, and we have beam stiffness and section moduli. You remember section moduli with the effective widths, and we have only life loads. Pedestrian uniformly distributed UDL life load, which makes our life a little easier. That's why I've chosen a pedestrian bridge, no concentrated loads. And of course we have a dead load. We start by choosing a cross-section, like in concrete we do. And then we try to prove that this cross-section is okay. Normally at the first try it's not okay, then we iterate, we see little bit top flange, bottom flange more, then we do it again. But here we have already a cross-section, I can assure you, which works. We go here a different way, roundabout, as in concrete. We start by calculating exactly the beam moments from life load by loading the bridge span-wise, in this case with the pedestrian UDL. And then of course we have a run-off moment for every of this configuration. And important here is the positive moments are as important as the negative moment. That's why we cannot use the beam on elastic foundation. That gives us only reasonable positive moments. So they have to be calculated by computer. Now, for this bridge, I can tell you they have been calculated by hand. And I very much enjoyed going through this statical calculations from 1960 or something. It was very nice. But of course, we need the precise ones. That's the difference here. We can't use a beam on elastic foundation. Then we combine the precise unit, the precise moments from the unit loads to a moment envelope from life load, so that at every say cable anchor point and midspan, we have the biggest and the biggest negative, so to say, moment from life loads. I think that's understood, you know, what a moment envelope is, combining all the unit loads so that we get the extreme moments at every point. So that's one starting point. Our chosen system has this life load envelope. Then, this next step, we calculate the moment capacity. What can the beam we have chosen take? Well, for that, we, of course, use basically the permissible stress times the section modulus. That is the moment capacity. And because we also have normal forces and in there, we say, okay, for the preliminary design, we use only 75% of the bending capacity to leave something for the normal force later on. Okay, then we come to the moment here, 75% of the permissible steel stress we used for SD37 times the section modulus at the bottom. So we have here, I just concentrate on this selected steel cross-section has a permissible moment plus, it should say plus minus 834 kilonewton meter. In the next step, we need to have, one could change the steps around. We have the life load envelope, and we need to know what comes in addition to the life load from the dead load. Now, basically what comes in addition is, we would say in German, the QL squared eighths are hung into the dead load, into the life load moment envelope. I've said here, okay, we calculate the dead load moment for a articulated system, which is the same. So we know we have then here 263 kilonewton meter from dead load. Okay, and now it comes all together. We now sum up the moments from life load envelope and dead load QL squared eighths, and compare those at every point with the moment capacity of the beam. And then we see whether we have to change the moment at the supports. So let's do it. We have the life load moment. We go into the first span here. And there we have the, that should be dead load, I'm sorry. We have plus 263 in the first span from dead load. We then had plus 817, I've repeated it here, from the moment, from the life load moment envelope. So if we just superimpose, without any additional cable shortenings, the dead load and life load, we come to plus 1080 kilonewton meter at that point. However, our permissible moment for the selected cross-section is only 834 kilonewton meter. So we need, from the third loading, which I call cable shortening, an additional minus 246 kilonewton meter at this point. So if we have it here all, it looks a little involved, but it's fairly simple. We have here the life load moment envelope. And then we have here, hung into it, the dead load, the 263. So we come here to this 1080. Now this is the permissible moment from the beam capacity here. And so we have to introduce a negative moment here by cable shortening, which has the amount of minus 246 here in the center of the span. Now, okay, then it's a straight line naturally. Then this must be minus 492 as a third moment from cable shortening. And if we do that for every space, we come to something like that. And we see now here we are just at the 834, Here we have something left. Well, that's not bad. Leaves us a little moment stress capacity. And then we shift these third part of moments due to cable shortening a little bit higher. We are free. We can choose any moment by cable shortening we want. N cables, n times statically indeterminate, n moments to choose. So at the end of all this, we then had a run of moments that's still in ton meters. It's a calculation from 1960, which I used here. But still, this is the run of moments. You see, we went here to times 10 to minus 605 at that time. We had here, I said, the 492, but there's some room to the 834, and about in the middle, finally, the run of moments was chosen. So we have reserve stresses here for something like 100 kilonewton meters, and of course then here at the bottom. And that would lead us to this run of permanent loads, which we wanted to find out. For a concrete bridge, this was the beam on rigid supports, QL squared 24th and 12th. Now here we have a rather different situation because of, in order to use a steel cross-section in the best way. And if we have this, then of course we can superimpose onto this dead load, permanent load situation, the life load envelopes, and we then come to this situation. This is a range, the biggest moment from dead and life load. You remember 803 we could have, now we end up with 724. Here we have 621, again less than 800. So we are well now within the range of the permissible moments for our chosen cross-section. Sounds a little bit strange on the first glance, I'm pretty sure, but we have to try to repeat the basics. Because we are free. Now I do it the other way. In concrete, our border condition is we need a run of moment under permanent loads which is not subject to creep. So we have a constant moment run of permanent loads. If it would be subject to creep, then we have to cover and size for one run of moments at opening for traffic before shrinkage and creep, and another one after shrinkage and creep. And that would give us a wider range of moment to size and would require more material. So we don't want that. We want a constant run of moments under permanent loads. And for concrete, the only run of moments which is not subject to creep is that of a beam rigidly supported at the cable anchor points, which I took great pain to explain to you in some earlier lecture, but this is now how we do it numerically, so it's not just a theoretical consideration. For a steel bridge, we do not have the problem for creep of moments. So, we go for the absolute minimum of steel quantity and choose a run of moments under permanent loads in such way that in superposition with the life load moments, we have a minimum of steel required. I've shown it to you for a simple pedestrian cable stayed bridge with a symmetric top-bottom flange cross-section. Now, road bridges, of course, have a wide orthotropic deck, which has much more, for a minimum cross-section already, much more material in the top flange than in the bottom flange. The bottom flange just has the minimum required and is smaller. It's only the width of the box without the usual cantilevers the top flange has. So, for a usual road cable-stayed steel bridge, we introduce rather high negative moments under permanent loads from the different moment capacity. And in the script, I have shown you several examples for cable-stayed steel bridges with these different types of selected moments and moments due to cable shortening, where this becomes very clear. So also I can recommend to you strongly, especially for this, that you read the scripts after I have told you the basic story here. Now we can go on with looking into the run of moments for some special cable-stayed steel bridges. We do that very briefly. If we have the life load only in the main, if we have only one backstay cable and we have the side span support, if we have only one backstay cable because the side span is supported on piers, well then it's rather simple. The dead and life load in the main span goes into the backstay, and there is no compression in the backstays from life load in the side span, because the life load in the side span is directly going into the supports, into the piers, makes it much easier. If we have a harp arrangement, we have the difference that a force here is transmitted by the tower to the top and bottom. So we have bending in the tower. That's the only difference for a harp against a fan arrangement. We need the bending stiffness of the tower to distribute the cable forces. If we have piers in the side span of a harp, like the knee bridge across the Rhine River, then life becomes much easier, because then every cable, forestay cable force, goes directly into the backstay without, so the backstay cable is only acting for this forestay, and every other cable here is its own backstay because it's rigidly supported, fixed to the beam. And finally, sometimes we have A towers, longitudinal A towers. Then the tower head is retained by the stiff A frame. So, a force acting on a cable here then runs through the cable and then goes directly into the foundation through the tower head in tension and compression. So this stands in itself. So it's a good system if we have a series of cable-stayed bridges where we don't have the usual backstay cable to keep the tower head in place. There, one good possibility is to use A towers, and then every intermediate system stands in itself. I think you have now a better understanding, after we've explained the backstay function, how vital it is for a cable-stayed bridge. And if we don't have it, because we have several cable-stayed bridges, one behind the other, then we replace it by an A tower.